will be some definitely some overlap. But again, my opinion is it never hurts to have overlap in stats or to have redundancy. It really just helps you, as you said, it reinforces it. So, you all remember simple linear regression, right? One predictor, how many outcomes? Simple linear regression was what, everybody?
1 to 1.
1 to 1, we got it. One predictor and one outcome. Multiple regression was 2 or more predictors and one outcome. Those you've already learned. We're going to get it again. And then this will be new in this chapter. Multivariate regression. Multiple outcomes and multiple predictors. And this really captures, multivariate regression will really capture the flavor of a multivariate technique. What you should see that is why is multiple regression even in a multivariate book? You've already had it in other classes. Because it still is a multivariate type of procedure because there's multiple predictors. So if you really take the notion of multivariate stats in a very global sense, really take it in a very global sense. X1, X2, X3, Y1, Y2, Y3. Multiple regression is just this. Right, everybody? Multiple predictors, one outcome. Multivariate regression. If I do all the arrows, right, maps each of the predictors onto each of the outcomes. So you could make an argument that any combination of multiple x's or y's could be a multivariate technique. Usually when people think of multivariate stats, they usually think of multiple outcomes as really starting to designate multivariate stats. But you do have multiple outcomes, multiple predictors, and that's a multivariate technique. Again, I know you've had multiple regression, but can I assume it'll be nice to have a little bit of a refresher for everybody? So multiple regression comes up a lot. Let's do just a brief primer on simple linear, just to get you back in the speed of view. I do have a database, everybody. It's called Health Survey _ in-class examples for semester. I'll be using this a lot. For the in-class examples, and I've appended it on Moodle. Plus your homeworks will be one database that I have appended that you'll use for homework throughout the semester. So here's the database. If you want to confirm anything in the notes, the database is right there on Moodle. It's right there on Moodle. Sorry. Does dieting predict exercise, or does exercise predict dieting? Does dieting predict exercise, or exercise predict dieting? I don't know. But tell me, with regression, you have to go ahead and create a model. So, what do you think? Go ahead, everybody. Someone come up with a model.
Let's go with dieting predicts exercise.
Which model did you choose? Okay, tell me why.
Because when you make the decision to diet, the emphasis is on losing weight, therefore you are restricting calorie consumption and increasing exercise.
Absolutely. Excellent argument for that. Can one argue that exercise predicts dieting?
No.
Make an argument for that.
When you increase your physical activity, you decide that to not have that be a wasted effort, you're thereby going to reduce your calories.
Good. Excellent. So do you see both of those are competing but plausible models? And that's a big part of multivariate stats. All of a sudden, we're dealing with multiple x's and or multiple y's. And there can be multiple hypotheses, multiple models, each of which may equally fit the model. They may equally fit the model. It's called equivalent models. But you may have very different stories. So here, let's go ahead. There's the correlation, 0.536. Again, everybody, when we say small, medium, and large, very, very, very context dependent. What do I mean by context dependent, everybody? But small, medium, and large in psychology may be very different than chemistry or physics or anthropology or business or management. In fact, I read a recent journal article that was pretty much saying, I'd love to get rid of these small, medium, and large taxonomies. And even in Jacob Cohen's book, every chapter, he says, this is just based on some studies in education and psychology. They may be different for your field. But for now, everybody, let's go with this. And we have a 0.536 correlation of exercise and diet, which is what? Small, medium, or large? Yeah, it's a large correlation. And if I square that sucker, 0.536 squared is 28% of the variance category. Remember, this is all rehashed from 6022. So the R squared is looking pretty good. If we square the correlation, where 1, 9, and 25% are small, medium, and large, again, this is a large. Which means how much is unexplained? Yeah, 71, which is kind of a lot, huh? So there's your R squared, everybody, for simple linear regression. And here what we have is exercise predicting dieting. We're going to have exercise predict dieting for this one. Here's the ANOVA, which breaks down the sum of squares. I mean, you now know that matrix algebra can actually help get at sum of squares. And as we know now, after chapter 2, matrix algebra can be used to derive sum of squares. So again, how to go through this? In SPSS, as you know, you just go to the linear regression option. You put in the independent or the predictor there, the dependent or the outcome there. Or if you're doing validation studies in psychometrics, they'll call it predictor and criterion. And as you already know, the sum of squares is regression over total. Sum of squares is regression over total, and you can get the R squared by the sum of squares. 28.8. So that's, again, all rehashed just for good old simple linear regression. For simple linear regression. And as you recall, you do get the parameter estimates. What are the parameter estimates again, everybody? The slope and the what? Slope and the intercept. Okay, tell me again what slope was.
It's how much it, for each 1 unit on the x-axis, what's the increase on the y-axis?
You got it. Change in y, given unit, change in x. You got it. Change in y, given change. Or, remember what some people used to say? Rise over run. Right? Rise over run. So, there is one thing I do want to say from your ANOVA. Do not print 0.000, right, as a p-value. It doesn't end. Even though some books may do that, either say what your alpha is, though some journals may say 0.001, as we discussed last week, would be ludicrous is to double click on them, which I did. If you did that AP journal, they what the heck are you doing? So you could probably just say 0.05, but I guarantee you, medical journals and others will say 0.01, because they'll want you to do it to the lowest feasible p-value that's often used. So again, look at the degrees of freedom. If we have one predictor for simple linear regression, the degrees of freedom is 1, and the denominator is n minus k minus 1, which is 146 minus 1 minus 1, 144. There's your f value, and we do have significance when we look at the ANOVA, right? Does everybody see we have a significant solution? Now this is testing the R squared, right? This is basically testing the R squared, because it's sum of squares regression over total. And we see it's significant. 28% is significant, and there's the slope. What does that mean? Using Chad's exclamation about it, as I go from 1 to 2 hours exercising, 2 to 3 hours exercising, etc., or my perception of exercising, my diet goes up by 0.47. And just so you know, everybody, just so you kind kind of get an idea of what these items are? Exercise is something I plan with my weekly schedule. Exercise is important to me. I often exercise to maintain or control my weight. So it's just a sum scale of all this, a mean scale. Diet. I try to avoid eating fast food and other junk foods. I try to eat healthy on a daily basis. I'm aware of the nutritional content of the foods I eat. So there's your exercise scale and your diet scale, each of which are made up of 3 items that are just averaged. How can I tell from my confidence interval around the slope that we have a reject with null decision? Because it doesn't include 0. Remember, if a confidence interval includes 0, right, then 0 is not included, you have significance. Again, change in y based on change in x is the slope, or sometimes called the regression coefficient. So this is the real world value of the metric. This is the real world. But do you all see the standardized coefficient of 0.536? Does everyone see that? Which is what? How is that interpreted? Standard deviation change in y based on standard deviation change in x. And as we know from 6022, for simple linear regression, guess what? Standardized coefficient equals the correlation. B equals R. It's the same, everybody. So again, B is this, and people use sometimes different notation. APA, sometimes they'll italicize it or call it beta. So B is the standardized coefficient, and it's the standard deviation change in y based on standard deviation change in x. So which one do you think? And the book discusses this. And again, the chapters in Grimm and Yarnell will be wonderful for supplementing this. So this already gets into the chapter on multiple regression and correlation on page 19. And I highly encourage you to read these chapters because they'll really be a wonderful supplement to Stevens. But the standardized coefficient versus the unstandardized one, which one is in the real world value? Standardized or unstandardized? Unstandardized. How many people understand what standard deviation change in y based on standard deviation change in x? Yes. It depends on how well they know the metric. If I have a standardized coefficient of 0.536, it means that a standard deviation change in x results in about half a standard deviation change in y, right? It's 0.536. So to interpret this, one way to interpret B of 0.536, right? Standard deviation change in y is associated with 0.536 standard deviation change in x is to be intimately familiar with the standard deviation, right, of x. Think about it, everybody. Let's go back to the descriptive stats. Do you see that standard deviation of x? And again, keeping in mind that we're using exercise to predict diet, x equals 1.169. So 0.536 times 1.169 will give you an idea of the change in y based on a change in x in the metric. So 0.53 is about 0.8 of a point percent. So again, that'll kind of give you an idea of how to associate it. But it's a lot of work to the consumer, isn't it? So again, which one reflects the real world values, everybody? Yeah, so real world values reflected per Grimm and Yarnall in the unstandardized coefficients. You got it. Here's your scatter plot. Does it look positive or negative? Positive. And ultimately, the type of estimator that's used is called ordinary least squares. Why? We try to minimize the squared error, which is y minus predicted y. Remember from good old 6022, the score minus the predicted score is the error. So, for these people, we've led everybody. For those below the regression line, we've went over or under predicted? Over. And these people we've under. Have some of them, have we done a pretty good job of predicting some of them? Not so hot for that one, huh? So, what we're trying to do is minimize, right? Minimize the error. And this is actually referred to, sometimes called as the loss function. And OLS does a pretty good job for these models, and it's sometimes referred to as the best linear unbiased estimator, literally. Unbiased means, you know what? The fact is, yeah, there'll be some overestimation, underestimation, but on the average, they'll come pretty darn close to the population coefficient. So what we want to do is minimize the error for simple linear or multiple linear regression. Here, as you recall from 6022, are some basic descriptive stats of the residuals and the predicted score. The mean of the residuals will always be what, everybody? 0. And standardized residuals just converts it to a mean of 0 and standard deviation of 1, so it's like a z-square. The standardized residuals, as you recall, are very important in looking at assumptions. Very important in assumptions, as you may recall. So, do you recall one of the assumptions? We wanted what? Normality of the outcome or normality of the residuals? Yes, normality of the residuals. It's nice to have a normally distributed outcome, but that's not the assumption, right? The assumption has to do with the errors, the residuals. So, how do they look? Not bad, huh? Right? So again, the main assumption, the main distributional assumption has to do with, what does E mean, everybody? Error. Error. You got it. You got it. Exactly. Below gets at the assumption. Remember the other assumption, everybody? Yes. Remember good old homoscedasticity? He did this millions of times in 6022. And what you hope is when you put the residual against a predicted score or the individual predictor for simple linear, you hope that when I impose that line, what we call the lowest line, the non-parametric line, we hope that was kind of straight. Because that means the constancy of variance. The constancy of variance in residuals is the same across the x-axis. Again, to use the example that I used previously, if these are your errors, which is y minus predicted y, and the mean of errors is always 0. And let's say this is income, from 0 to $100,000. This means, in your opinion, do the errors look kind of constant? And does the variability of the errors look pretty similar across all levels of income? What if you had something like this? Uh-oh, so for some reason, at $50,000, you have a lot of negative residuals, which means you've over-predicted. I remember if you have a negative residual, you've over-predicted. If you have a positive residual, you've under-predicted. So something weird is going on here. at middle levels of income, let's say my DV is depression. Maybe at middle levels of income, for some reason they're not as forthright about depression. That being said, everybody, what's your opinion if that was your data? This is just a visual opinion. So look good or look bad? Looks good.
Pretty good.
You got it. I agree with you. I agree with you. And as you know, as we discussed many times last semester, you can use the lowest option in regression. The lowest is called locally weighted smoother scatter plot. And that is a type of non-parametric regression which literally conforms to all the bends and the curves of the data. And I'd say we're doing a pretty good job here with diet and exercise. So do the residuals look good, yes or no?
Yes.
Did the residual plot look good?
Yes.
Absolutely. I agree with you. And one last graphic. Just to be on the safe side. And let's look at linearity again. Again, we've got exercise predicting diet. So you go graphs, scatter, simple scatter. We have exercise, predict diet. You've already imposed a line, but I'd like you to tell me if you think we have a potential nonlinearity. Okay, there we go. So as you practice many times, let's go ahead and just impose, instead of a linear line, we've already got that, let's impose the lowest. How's it look, everybody, for linearity? Let's look at linearity of x and y. Let's say it looks pretty good. I think it looks pretty good. Is there anything that would indicate a quadratic? I mean, you could, if you wanted, let's say you say, well, I see that little curve. Let's say you were kind of really wanted to really get that little curve. So let's go ahead and put linear, apply, and then let's put quadratic. Okay, does quadratic help much? In your opinion, not even thinking about statistical significance testing, going from 28.8% to 29.7%. So basically increasing 1%, 0.9 of 1%. Is it worth it? I agree with you. I mean, yeah, it's not, I mean, it is better than the linear, but then you have to make one of the decisions. Is it worth to make the model more or less complex? If I add a quadratic term, am I making it more or less complex? Yeah. Because now, if you wanted to fit the above, right? If you really wanted an extra 1% in your equation is y prime, y predicted equals b, 0, which is the intercept, plus bx, 1, plus what else did I put? Bx1 squared. So is it worth it? Probably not. Even if it was statistically significant. Say you had 6,000 people in your database because you were able to get a huge secondary archival database from Center of Creative Leadership. So that 1% is significant. I agree. I absolutely agree. So that's, again, everybody, Just your good old garden variety, simple linear regression. Multiple regression is just two predictors. As we went over many times in 6022, but I am going to show you some of the matrix algebra. I'm going to show you some of the matrix algebra from regression analysis. Again, you will not have to do the matrix algebra. I just want to show you where it comes from. So this is a true multivariate technique if you consider multivariate to be either multiple explanatory or multiple response variables. So first, let me briefly show you the black box behind this. Let me show you a little bit of the black box behind this. And let me see which example I have here. Do this real quick here. I do have all these handouts for you, everybody. I want to see which one I've got here. Okay, great. You will not have to worry about this, everybody. But I just want to show this to you really quick. And you can see where matrix algebra enters into multiple regression. So taking a very, 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 very small data set, let's take y. 3, 2, 4, 5, 8. A very small data set. And let's go ahead and have the first predictor, which is 2, 3, 5, 7, 8. And let's just say these are self-report scales of job satisfaction, job commitment, and job stress. So now we got 1, 5, 3, 6, 7. So there's your data, everybody. There's your data. So did everybody see we have two predictors and one outcome? We have two predictors and one outcome. Which means, and this follows, just so you know, everybody, this follows from the book right there. This is the same data, page 69. So you can kind of follow along and see how it goes. So now you've got this data, everybody. And then what you want to do is you create the matrices. So you actually have a Y matrix. That's a Y matrix. Is that a row or a column vector?
Column.
You got it. Excellent. It's a column vector. You got it. So this is a column vector. And then you have, if I can bold X. Now this is going to seem kind of weird, everybody. How many variables do I have here? How many predictors? How many vectors? How many predictors in this one? 2, right? 2 predictors. But my X is going to have 3 columns. That is a universal notation for the intercept. You're going to see a vector of 1. A vector of 1 is just the traditional way you're always going to see matrix algebra. So it's a constant. So you're going to see this many times in statistics and multivariate. And you're going to see a column of 1s and say, oh, there's no 1s in my database. I don't see any 1s there. It's for the intercept, to capture the intercept. And here you have a column vector of your parameter estimates. The intercept, can someone remind me what the intercept is?
Where it crosses the y-axis.
Yes, when x is 0. When x is 0, where does it cross the y-axis? Right? When x is 0, where does it cross? The y-axis. That's the intercept, which is heavily influenced by what, everybody? The means. So there, you see you have the matrix. You have the column matrix of y. I'm going to put this right here, just so you know I'm going to focus on that. which will equal xb plus. What do we always have whenever we predict something, everybody?
Error.
Thank you. You got it. There's your matrix setup. There's your matrix setup for multiple regression. There's your matrix setup for multiple regression. So, how do you get at this, everybody? The regression coefficient, the good old beta. And again, this is from the book. You will not have to do this for homework. The beta is a function of x minus 1. And again, you can see the notation. I believe it makes it clear here. Yep, times x prime minus 1. What the heck is that, everybody? Let's focus on this second part here. What does this mean again?
Transpose.
Yes. What is y?
The vector.
D. This is only including what? Only the ivies, right? This includes the transpose of x times x. So when all said and done, what does the minus 1 mean, everybody? Inversion. The inverse, which is kind of analogous to? What's the definition of a slope? Change in y based on y divided by x. Do you see that? Remember, this is in the numerator. This is in the denominator. So the numerator takes into account x and y, whereas the denominator kind of gets at. There you go. But you got multiple variables. You got multiple variables. So here's the basic setup. The basic setup for regression. I'm not going to go through all the math because the book shows it already. But if you look on page 70, everybody, if you look on page 70, it shows you the transpose when you do x times the transpose of x. It gives you those numbers, 5, 25, 22, etc. And then you go ahead and take x times, and then x prime times y. Again, x prime would be 1, 1, 1, 1, 1, 2, 3, 5, 7, 8, 1, 5, 3, 6, 7. And here you've got the transpose of x. So you're going to take this times this. And we already know that they're conformable. Why? Because we know we see that we have 5, right? 5 here, and we have 5 there. Then, what the computer does, and what the book shows you in some detail, is how to get at each of these. And do you see on page 70, when all is said and done, you have 1016. Do you see where x prime, you divide by 1016? Guess what that probably is? When you divide, it's divided by what?
The determinant.
The determinant. You really want a computer to do that, everybody. Right? Why do we want a computer to do it? It's not just a 2 by 2, is it? So you have to do all these cofactors and elements, and you really want a computer to do that for you. So, now, using 1 divided by 1016 by this matrix, by the combination and the multiplication of this, you can get at all your regression coefficients. You can get at your regression coefficients, and you see it's 0.5, 1, minus 0.25. And let's see where we got that from, everybody. Let's see where we got that from. This is in your handout. Here you have y, x1, x2. Here you have the correlations, 0.89, 0.6 with the outcome, pretty darn good. I'm going to be very concerned about that 0.8 when we get to the section on linearity. I'm going to be very concerned about that 0.8. The R squared, is 82%. Small, medium, or large? Large. In fact, if that was real data, I don't want to say it's too large. I mean, it's good to have large, but that's almost too large. I'm wondering, are there some linear combinations there? Again, no hard and fast rule, but for multiple regression, small, medium, large effect size, and this is for multiple regression, will be 2%, 13%, or 26%. 2%, 13%, or 26%. Small, medium, or large. That's a large effect size. And compare this to your book, everybody. Compare this to your book and the derivation. It's exactly what matrix algebra resulted in. There's your intercept. 0.5, same as the book if you go through all the math. 1.0, x1 is the regression coefficient for x1. Negative 0.25 for x2. Exactly what we have from the book. Exactly what we have from the book. So there's your full equation, everybody. There's your regression equation, which is derived via matrix algebra. This is the big part of it, everybody. Calculating the coefficients takes the matrix of the transposed x times y over the transposed x times the actual x. That's it. So really, even though I've shown you different ways of deriving the 6022, this is actually how it's done in the computer with the matrix algebra. It's all matrix algebra. So the full solution here, everybody, full equation, is 0.5, which is the intercept, plus 1.0 x1, plus negative 0.25 x2. And that's the full equation.
So that puts us in the equation. Can we solve from there? Or is that?
I'm sorry, say that? What do you mean, what can we solve?
Is that the final step? Or can we solve, once we've got it in that equation, can we move forward?
Absolutely. Once you have that equation, then what do you get from that? A predicted score for each individual. Right, remember you get a predicted score for each individual, plot it, you get the residuals, absolutely. Because you plug in your scores. You plug in the x1s and x2s. Now, what's a little confusing, everybody, does everybody see x2 and y as a negative regression coefficient of negative 0.25? Which means as x2 goes from 1 to 2, 2 to 3, the dv goes down by 0.25. But can you explain to me how the heck do you have a negative coefficient and a positive correlation? Does that seem a little weird? You have a positive correlation and a negative coefficient. Because when you have this thing called linearity, overlap of predictors, things get really screwy. And when the sign reverses, you may have what's called a suppression effect. And we'll talk about suppression in this chapter. So things can get really weird with multiple regression when you have highly related what, everybody? Yes. And that is, it really is, that the vectors in that matrix algebra language, these two vectors are highly related. They have a correlation of 0.813. Right? So when you have high linearity, such as here, 0.814, you get really screwy results. Right? Really screwy results, such as reversal of sign or a suppressor effect. So everybody, there's the ANOVA, which shows the R square for multiple regression. How do I know it's multiple regression? 2 degrees of freedom means 2 predictors. And as you know, I can break down the sum of squares. I can break down the sum of squares as the book starts on page 71 and get at not only R squared, but I can get at R, because once I take 17 divided by 21 and take the square root of it, that's R. I can get at the standard deviation of variance. Can someone remind me from this output how I can also get the standard deviation of variance of the dv? anyone remember? And as well, standard deviation and variance of y. Can anyone remind me how I can get at the variance and standard deviation just from this table? See if you can remember this. What divided by what will give me the variance? Take 21.2 divided by 4, please. In your calculator, tell me what you get. Take 21.2, sum of squares of total, divided by 4, what do you get? Do you get about 5.3? Take the square root of it, please. 2.3. Does everyone see sum of squares of total over degrees of freedom is the variance, the dv, and then when I take the square root, standard deviation, and there's your 5.3, there's your variance. So what's kind of cool about the sum of squares, which is derived, as you now know, via matrix algebra, you can get at the r, according to the r squared, the standard deviation, and the variance. All of that can be derived. Again, as a reminder, everybody, the sum of y minus the mean of y squared is total sum of squares. Each individual score from the mean. Y prime, predicted y, minus the mean of y, gets that regression sum of squares, the good stuff, right? Because you want things to deviate from the mean. If I were to use this predictor, I might as well just use the mean to predict the outcome, which means it's not a very helpful predictor. If I want to say how much cash you guys got on you, and let's say you have 10 bucks on you, and I have a really good predictor, I should get pretty close to 8, 10, 9, 12, 15. If I use this predictor, I might as well just say 10, 10, 10, 10, 10. So we actually want more variability with sum of squares regression, because it means my predicted score isn't exactly equal to the mean. I mean, yes, you could predict 68 degrees for many days in San Diego for the weather, and you'll do okay. Some days you're going to radically what? Over-predict? And some days you're going to radically? Yes. Then y minus predicted y is the residual, the bad stuff. It's the deviation score, so to speak, from the actual y and what you predicted from the equation. And then, so that decomposes the sum of squares, as we went over many times in 6022, and you actually got experience at calculating it, shows you how to break down the variance. And the f, the test statistic ultimately, is a function of the mean square of regression over mean square of residual. Or, equivalently, r squared divided by the number of degrees of freedom divided by 1 minus the r squared divided by sample size minus the number of predictors minus 1. Both of those will give you the same exact result for your f statistic, which is 4.653. So if this was a real data set, everybody, using alpha of 0.05, would you reject or fail to reject the overall solution? For the two predictors, even though it's only sample size of 5, would you reject or fail to reject? Given an f of 4.653, degrees of freedom of 2 and 2, and a p-value of 0.177. What's that? Fail or reject? But we have a big effect size, you guys. How does that jive? Wow, we accounted for a lot of variance. We accounted for a good chunk of variance from this, and yet we don't have significance. Yeah, you got 5 people. So what would you tell someone? If a client collected data on 5 employees at Qualcomm and said, you know what, we got a nice effect size. We got 70, 80% accounted for. We don't have significance. You probably recommend them what?
Do power analysis.
Okay, do a power. And get more people, right? I mean, 5 ain't going to cut it. Is there a chance you got lucky on this big effect size by luck of the draw of those 5 people, right? So that's why be very wary about trusting fit statistics with small samples. And then, very briefly, again, you're not going to have to worry about this, but I just want to show you some of the matrix algebra the standardized coefficients. Just briefly, some of the standardized coefficients. And I believe I have this in your handout, everybody. Yep, I sure do. Yes, I've given you all, yeah, I've given you a lot of stuff for handouts, everybody. So hopefully, I don't know if you've accessed them, but it'd be really helpful for you to start printing them out, bringing them with you, because they'll be nice guides as I go through. So, now, you know how to get the standardized coefficients via matrix algebra. But what about the standardized coefficients? How do those play a big role? Let's say we have motivation, quality of your work, maybe your grades, to predict some type of comprehensive outcome. So you have 3 predictors and 1 outcome. There's your correlation matrix, everybody. There's your correlation matrix. All those variables. Okay, so there's your correlation matrix. So in your opinion, do they have an okay relation with the DV? 0.59, 0.7, 0.75. Do they seem to have a nice substantive relationship? So that's the first thing you want to look at with multiple regression. How's the relation to the predictors? But do we have some potential problems with linearity? Do you see that 0.78? That's pretty high, grade and quality. So, how do I get at some of the other estimates? How do I get at some of the other estimates? Well, let me see what I included from this. In the older version of SPSS, you used to get these a little bit easier. Let me see if I get any of these. Here's the basic groundwork. And again, I'm going to write this kind of quickly, and there's no way you're going to have to worry about this, everybody. Let's say this is grade, motivated, and qualitative. These are your 3 predictors. Grade, motivation, and qualitative. Again, you're not going to have to worry about this. And 2.62, negative 0.204, negative 1.97. And basically, I've got all these numbers. And what are they? R minus 1. Would anyone like to guess what that probably is? The inversion of what? 3 variables are regression. What? Regression. Correlation. It's an inversion of a correlation matrix. Right? So basically, the matrix algebra behind these multivariate stats will take an inversion of this correlation matrix. And you can actually get that in SPSS. There's the correlations, and you can actually invert them. So, once I invert them, then what I can do is get into so look at the matrix algebra. I get this correlation matrix, I invert it. If you ever want to see how I did it by hand, you're more than welcome to take a look at this. Probably would be of much interest. There's the correlation matrix times y. So essentially, if I go through that math, everybody, which was a little on the painstaking side to do, it didn't take me that long to do it, but you have a regression, you have your correlations, right? Does everybody see these correlations? You invert them, which means you got to find the determinant of the correlation matrix, multiply by y, and all is said and done, everybody, that formula there gets me this. That formula. We already know how we get this from matrix algebra. And now you can get this because the standardized coefficients are a function of the correlations, and correlations are a type of what? Standard or non-standard score. Correlation is a standard or unstandard score. Standard, absolutely. The type of standard score. You got it. So, even though I'm not going to go through all the math right now, there's the standardized coefficients. And just so you know, everybody, once you get the unstandardized one, it's easy to calculate that. Because beta, the standardized coefficient, beta is essentially small beta times standard deviation of x over standard deviation of y. It just reverses that. Because as you know, the usual beta is the correlation of x and y, standard deviation of y over standard deviation of x to calculate for simple linear regression. For the unstandardized coefficient, the standardized, you just take that unstandardized and just flip the standard deviations. And it gets you all these standardized coefficients. And that's how you calculate it, everybody. That's how you calculate the standardized coefficient. And the big matrix part of this, everybody, is a matrix of what, everybody? Correlations. A big part of this. So as you see, and a major part of the computation for standardized coefficients is the R correlation matrix, where we see that B I equals R minus 1 R I Y. So it's nice to have computers do that. It wasn't that hard for me to do the 3 predictors. If you had that much more, it's just let the computers do it. Do you again see the role of matrix algebra? Okay, how did we do, everybody? 70% of variance counted for. Small, medium, or large?
Large.
Large. Not bad. Which predictors, if any, are significant? This is in your head now. Are any of them significant?
No, none of them are significant.
No. But we again have a small sample size, right? If we look here, everybody, we had 6 people. So once you have more people, then we'll get more of the significance testing. And your homework will have much larger sample size. So that is kind of showing you briefly some of the matrix algebra for multiple regression, both the standardized and unstandardized coefficients. We're going to talk briefly about the role of standardized coefficients. Some people use those to rank order the importance of predictors, and there's a lot of problems with that. A lot of problems with that. So again, interpreting this as motivation goes from 1 to 2, 2 to 3. The DV goes up by 0.658, controlling or parceling out the other predictors. Don't forget that, everybody. It's a partial correlation. It's a partial regression coefficient. It's parceling out all the other variables. So visually, don't forget what it looks like, everybody. When you have this multivariate system, when you have y, x1, x2, x3, if I want to look at by1 dot 2, 3, it's a relation with y in 1 partially out 2 or 3. All right? That's the notion of partially out the regression. So don't forget that, everybody. And we'll turn briefly soon to the partial and semi-part correlation. And I know you remember those from 602 but we'll get into those again in a few minutes, just to make sure you remember them. I believe the model, it does talk about that. So, this is actually ad calculations I did to get the regression coefficients. It's called the swept correlation matrix. Something you will never, ever, ever have to do. But the above, okay, I do have it here. BI is the column matrix. Standardized coefficients. We have RY1, which is the inverse, and R, which is a column. There it is. So what I typed, I already have it for you guys. So, in other words, now matrix algebra completely gets into the standardized and unstandardized coefficients. Let's discuss one of the big problems, linearity. It's not going to impact just multiple regression, but almost every technique we will use in the semester. Whether MANOVA, Vankova, canonical correlation, structure equation, log. R and regression coefficient will be limited or unstable in linearity. Hard to ascertain which predictors will wield the most importance. If you have highly related variables, it's hard to know which one does the best job. In other words, if I have something like this, y, x1, and x2, and let's say the correlation of those two is 0.65, do you see this overlap right there, everybody? And once you partial that out, it's going to be hard to say which one has the most contribution. And that's a big problem in these types of multiple input models. So let's say math has a correlation with the outcome of 0.43. SAT math has a correlation of 0.49. So you have a math GPA and an SAT math. Do you think those are going to be kind of correlated? Do you think maybe your math scores through high school and your SAT math? Let's say we have a correlation of 0.743. To the extent that SAT may be significant, math GPA isn't, even though both are similar. There is a chance that this will be significant in regression. This will not. The degree, they're both kind of similar. I mean, in the real world, if you told your boss, we had a correlation of 0.49 for one variable, 0.43, if he asks you, well, were they similar or different, what would you probably say? Similar. And yet one may be significant and the other isn't because of that, 0.743. So you see where things get really screwy and unstable in the event of linearity. And this impacts every single multivariate technique we'll use throughout the semester. So multipolarity is highly related. Singularity is the example that we use for matrix algebra. When you have a correlation of 1.0. When you have a correlation of 1.0. Look at x2 and x3 below. You see that 1.0? That would be a problem. Huge problem. So what did I do to create that variable? I just had it be a score and a total score. Because the score is used in the total score. How many variables do I have as predictors here, everybody? X2, 3, I have 2, right? So everybody see I have 2 predictors? Look what SPSS does. Linearity is present. The following variables were not included, etc. Guess what it got rid of? X2. And I never like the computer to decide which variables will be incorporated or not. So guess what? When there's linearity, the computer will do it for you. It'll check it out. Because can you divide by 0? No. And that's what happens with linearity. So one option, there is one, some of the options the book presents, one is called ridge regression. I think I've used it once. I mean, in all the years I've been a statistical consultant, I've used it once. There's no point and click for it, but there is a macro. There is a macro in SPSS called ridge regression. Basically what it does is it adds a little constant to the variances. It adds a constant so that you don't have the problem as much by an correlation. I just want to show you what the language looks like. You never have to even access this. But as you know, you learned last week about Larry DiCarlo's macro, and I do want you to run it for the regression homework, which I'll go over soon. Here, all you have to do with all these macros is use an include statement. You just do an include statement where you say where you saved it. And here's an example, everybody. Here's an example. When oops, 0.77, 0.7, job involvement, organization commitment, conscientiousness, one of the big 5 at job sat. We got some linearity there. In fact, this is almost the worst case scenario. And I'll tell you why. Correlations with the outcome are low, and the intercorrelations are high. That's almost your worst case scenario for regression analysis. I hope it doesn't happen in 25%, not bad. Not bad. None of them are significant. None of them are. And here's where things get really screwed. When you look at the zero order correlation, look at conscientiousness. We got a negative 0.09 correlation of conscientiousness and job set. The partial is negative 0.4. How can you partial something out and it gets bigger? That would be like you giving your spouse $5,000 and your bank balance is bigger. I mean, that'd be great, but it's not going to happen. That's almost what it seems like. And that's when you get really low correlations with Y and X, and you get these really screwy results. So here's how to use ridge regression. You just find wherever you keep your file, and here's the syntax. A couple lines of code. Just enter your predictors, and what it does is it gives you estimated values of k where it adds a constant. So it basically adds a constant. And you kind of can see where r squared, some of that is the lowest or the highest. And you kind of get an idea for when it adds a constant. And these are the regression estimates. And basically, the idea in ridge regression is one of compromise. We find a small constant that increases the stability. So it's kind of weird, it's not used a lot, but here we found, for our example, our regression went down to 14.6% from 25%. When I use the optimal solution, which is right about here, everybody, 14.6%. So, that being said, everybody, I don't use ridge that much, but it is one option. Another option the book indicates is you can combine variables. If you're going to combine variables, as you'll learn if anyone's taking psychometrics, you're going to learn about a thing called construct validity. Be very, very wary of combining variables and pretending that they measure one construct. You may be fine, but you know what? You're going to have to do your due diligence before I just combine job involvement, job stress, job commitment, and create an overall job attitude scale. Because, wow, Dale, I found job involvement and job engagement have a correlation of 0.87. So I'm going to assume they measure the same thing. Maybe, maybe not. Maybe job involvement and job engagement are related and yet separate in their own right. So that's what you need to do, factor analysis, to do your due diligence on it. So one option is just to combine them. The other option is to just decide which one to use. I've done that. If I had SAT math and I had average math GPA from high school and it was a 0.8 correlation, I'm not going to combine them into a scale. That's kind of goofy. So I may just make a decision, which one do I want to keep? Right? I mean, I'll consult the experts, see which one would make more sense. Now you could make a data-driven decision, which would look at which one has the highest correlation with the outcome. But now it's a data-driven decision rather than something based on expertise. Time to class coach. 8:50. Okay, I got a few minutes. Just a few. I'll let you out. Here's your in-class database, everybody. Exercise, health maintenance, social influence, predicting diet. A little bit of linearity, not horrible. Okay, results with the outcome, not bad. So it's looking potentially problematic. 35% of the variance is accounted for. Thumbs up or thumbs down for the overall model. 35, you'd be pretty happy with that. If that was your dissertation, believe me, 35% you'd be happy with. Are any of these significant?
Yes.
Yes. Exercise and health maintenance. And then soon you're going to learn about the partial and semi-part, which we've gone over in other classes. If they don't change that radically, guess what? You probably don't have linearity. But I've seen one potential problem. Look at social influence. The correlation is 0.3. The partial is 0.034. It's negligible. And you know we'll shed influence into that, everybody? Looking at social influence and seeing that it has some of the larger correlations with the other predictors, 0.39 and 0.40. So that's kind of a little signpost into potential problems. So then, part of the collinearity diagnostic is looking at tolerance and the variance inflation factor. Tolerance and VIF, as you recall from 6022, was in chapter 10. But just to go over it, these will be very important diagnostics, not only multiple regression, but other statistics. Tolerance is basically each IV becomes a D. Collinearity only focuses on the X's. Okay? So, recall, linearity only focuses on the X's. So tolerance is a function of 1 minus R squared, with each IV serving as a D. The maximum value is 1.0. Can't get higher than that, everybody. So if you have So you would love to have R12 equals 0. Because 1 minus R12, and you square it, equals 1.0. Right? 0 squared is 0. So that means, how would I draw my picture, everybody? How would I draw my picture if I have an inner correlation of x1 and x2 is 0? Where will x1 and x2 be? Overlap or non-overlap? Non-overlap. They each explain their own unique piece of the pie. So tolerance, everybody, is one statistical index for linearity. As it gets closer from 1.0, you got problems. So there's your tolerance. 0.767, 0.775, 0.773. Because we know there's some intercorrelation. We already know that and actually I can figure out how much intercorrelation there is by working backwards. What's 1 minus 0.767? 1 minus 0.677 would be about 0.233. That means 23% of variance is accounted for with the other predictors when they're predicting the IV. So everybody, here, just to show you, some textbooks will say, don't worry about tolerance unless it's less than 0.10. But that means you have intercorrelations greater than negative 0.9. Right? Because think about it. If tolerance is 0.1, it means 1 minus that is 0.9. My own red flag, everybody, my own personal red flag, is if I see intercorrelations of about 0.5-ish and it's tolerance of 0.75. Because what's 0.5 squared, everybody? Right. And 1 minus 0.25 equals 0.75, so it's squared. So everybody, what I would like us to use is don't just use 0.1, but if you see any tolerances that are a bit lower than 0.7-ish, take a look at it. Take a look at it. The inverse of tolerance is the variance inflation factor. VIF, it's just the inverse. It's 1 divided by tolerance. That's all it is, everybody. And VIF is just the inverse of tolerance. So here we see 0.767 for exercise. 1 divided by 0.767 is 1.45. So the variance inflation factor is just the inverse of tolerance, which equals 1 divided by 1 divided by 1 minus R squared of ij, where ij may be 2 or more. So, as
magnitude closer to 1.0 is a good thing for VIF. Since it's the inverse, right? So, lower VIF and higher tolerance is preferred. So if we took the liberal stance of 0.10 tolerance to be problematic, 1 divided by 0.1 is 10. So some say VIF of greater 10 is indication of severe collinearity, but I think that's way too liberal. I think that is way too forgiving. So, which one to look at, everybody? When you go to SPSS, when you do regression, you'll see this option called collinearity diagnostics. You'll see the option when you go into Analyze, Regression, Linear, under Options, under Statistics, you'll see collinearity diagnostics. And it'll spit out all this. With that, I'm going to let you go. Be good, everybody. There is no homework assignment. Well, boy, that's a matrix algebra.
Can we get an early start on